Okay, now suppose if you keep on increasing this 2 to higher values, say 2 square, right? Now I made it to 2 power 20. What is the value? A huge number. So it will take, if I want to try, so 20 bits are there. So 0, 0, 0, somewhere 0, 1, like this 20 bits. So how many possible combinations? 2 power 20. So 2 power 20 is a very huge combination. So even though if I use the latest GPU and all, it may take years. Or say suppose, we don't know, say 30 days. Now if I make it 200 bits, 2 to the power of 200 bit combination. So it may take 1 year. But these 2 to the power of 200 bits, the information, the quantum computing can crack in 1 day or in 1 hour. So the number of combinations you have to try, say 2 to the power of 200. See, 2 square is 4. 2 to the power of 10 is 1024, 1000 combinations. So 2 to the power of 10, I think it is 1024. So 1024 combinations I have to try one by one. Suppose if I say 2 to the power of 20, 2 to the power of 10 into 2 to the power of 10. That means 1024 into 1024. See, this becomes a very huge number. Our computers, the classical computers, cannot do it. It needs years. But a quantum computing can solve this in 1 day max. Okay. So I shared one information in the group. Okay. So what it says? So if you see here in the quantum computing, so I shared one group on that information. Okay. So from Srinivas Padun. So here what he is telling, see here, there is a definite threat in cyber security, while huge opportunity in acceleration of quantum ML. So why he is telling that it's a definite threat in cyber security? Have you thought of why it is a threat to cyber security and why it is advantage to quantum ML? Because we have to break the key. Suppose, as I said, if it is 2 to the power of 1, 2 to the power of 10, 1024 key combinations. If it is 2 to the power of 20 means whole square. So this is a very huge number. Say 100 crores. So 100 crore attempts we have to do. Maybe one of them is my password. But we cannot do 100 crore trials. We cannot store it. We cannot run it. But quantum computing can do it in 1 day. You can just search in Google. So how is it possible? Just the data representation, it is getting changed, and how we operate on the data. That's it. These two are the two combinations. The way I represent the data, the way I manipulate the data is completely different, and we are getting these concepts from quantum mechanics. So we don't go much deeper into quantum mechanics or quantum physics. Okay, so this is what makes quantum computing. Okay, it's a that's what people are using quantum computing. It's just we need, why? Because we can solve. See here, cracking large encryption keys. If I want to search entire Aadhaar and I want to find out, if I give my image as an input to the Aadhaar, where it contains almost 100 crore people, or I don't know, 200 crore people are there. So if I want to search one by one and I want to get that information, classical computers may not work, or they may need time, but quantum computers can get that in at least max 1 day. Okay, see, simulating molecules in chemistry. So anything which I cannot see naturally, it means any operation, any huge operation which I cannot do with classical computing, I can do it with uh, quantum computing. So if you see here, one of the famous researchers says that nature, means the way we operate the data, the way we store the data, okay, is not classical. That means you cannot, it may not work with 0 comma 1 bits. Everything the classical computer stores 0 comma 1. It processes everything in 0 comma 1s. But if you want to simulate it, if you want to represent, or if we can say that if you want to work with huge volumes of data, then quantum representation. So you don't worry about or confuse about or fear about what this quantum and all. Only thing is the way we represent the data, the way we operate the data, these two will change, and that reduces too much of computation time. That's it. So see here, we'll go slowly. So in general, we use bit. Bits means 0 comma 1. That is what our classical computing. So in general, what happens if I take any variable? So that variable can be, okay, one place, one storage. Okay, it can store only one bit. Assume that. So in classical computing, we have 2 bits, 0 comma 1. So either the storage can store 1, or the storage can store 1 or 0. So this one storage, I can store only one value. Whereas in quantum computing, we can call it as a qubit, quantum bit. So it is having the property of superposition. What is superposition? You can store 0 information, 1 information. The bit can hold both the information. How it stores? So how it stores? See here, I am using, so this is how they represent the quantum information. Okay, so this is how they say this is a variable, the variable 0. That means x. If I say like this, that means quantum x, qubit x. Similarly, y. Now, if you see here, how I can store two values. So I can give some weightage, alpha is some weightage to the qubit 0. Don't worry, this and this, you assume this is 0. So alpha into this 0, okay, plus beta into 1. And the property is alpha square plus beta square equal to 1. That means the weight I'm giving it. So qubit, that storage, this storage contains the information about 0 bit and 1 bit. How much it represents the probability. See, at a time, I can work with only one value, but I can store, say, 40% of information about 0, 60% of 60 probability of 1. That means when I try to take this qubit, say, suppose if I represent the qubit as a combination qubit, some name I have given, some variable, qubit means some variable, nothing, hi-fi word, that's it, nothing is there. So what I'm doing is alpha into, this is the weightage, say 30%, into the variable 0, like we have two variables, that's it, beta into 1. The condition is alpha square plus beta square equal to 1. As of now, assume that alpha plus beta equal to 1. Then what happens? 30% weightage I am giving it to 1, and 70% information I am giving it to this one. Okay. So when I store it, the C contains both information, 30% 0, 70% 1. When I want to use in any operation, then it will realize. Realize in the sense, either it will store this one or this one. Because the probability is 70%, so the variable C becomes the variable 1. So realization, the place, this place is equal to beta. Suppose beta is 70%, right? So it is 1. Okay, that means it's like a magical coin. Any magical coin in classical, it is either head or tail. But in quantum computing, we assume that if I toss, both will be there, head and tail. But when we caught and when we see that, it is either head or tail. Okay. So when I'm computing, when I'm using it for any variables, it can store multiple values about 0 and 1. So that is what superposition. Don't worry, when we go further, we can try to understand. So see here, data nature, deterministic, it is either 0 or 1. But in case of quantum computing, it's a combination of two values, 0 and 1, and varying probabilities. It may be 1%, this may be 19%, this may be 10%, this may be 90%. In this way, the values will vary. Okay. So see here, parallelism. So why here I cannot do parallelism? Because see, one value only at a time. But here, intrinsic parallelism, many paths at once. Why? Because it can store two values at a time. So, okay, we'll see how I can represent. Suppose if I go further and see here, I can store two qubits also. So if I take 2 to the power of 1, then what happens? 2 qubits. That is 0, comma 1. So when I write 0, assume that I'm writing like this. This is just a representation. Okay. Now if I say 2 square, there are 4 combinations. What are those 4 combinations? 0, 0, 0, 1, 1, 0, 1, 1. So all these, see here, with the 2 qubit superposition, you can store a quantum state. I can have a quantum state, or I can have a register that can store all 4 states. That means 4 magic coins are tossing. Okay. So like this, the information, the way I represent the data, the way the operations like superposition, etc., I'm using. So see, I can, a single variable represent the all combinations. 4 combinations. So no need to try 4 combinations. This is enough. So that is how I can do computations in quantum computing. Okay. So no need to worry. Fine. See here. This is very good example. Classical. So my light, either it is on or it is off. That's it. But when we take quantum, see, it is dim plus ghost. It is dim. It is neither, means it is both the cases. So that is what makes the difference here. A switch is neither off nor on. It's both. And that is how I am using in the computations. So any doubts still here? Any doubts? Okay, so you may not get the gist immediately, but slowly try to understand. Okay, so now we just seen like alpha and beta. So what is alpha and beta? So alpha and beta decides the weightage, how much importance I'm going to give it to this one 0 bit, and how much information I'm going to give it to 1 bit. So when I'm dealing with only 2 bits, that means 2 to the power of 1 equal to 2 bits, I have this and this. So how much importance I'm going to give, that is called as alpha into this one plus beta into this one. Okay, so how to make chapati? So 30% atta, 70% milk. Same, that is called the state of the food. Same like this. So it contains both. Okay, and what is this? So this is the weight the qubits gives to each state. So this combining is called as superposition. So this combination working with, see, suppose say I just ignore this representation. So alpha into 0 plus beta into 1. So what I am doing, I am storing an information which carries weightage about 0th bit and the first bit 1. So two information parallel I can handle here. This combination is not possible in the classical. So this variable contains either 0 or 1. Okay. So this allows quantum computers, because I can handle, I can store, I can represent both the variables. So I can go parallel processing parallelly. Like suppose in your work also, if you want to prove the results, if you want to test your results, see nowadays what is happening, if I want to perform machine learning or deep learning results, suppose I want test with 300 images or 500 images or 1000 images maximum. So that will take huge amount of time. Suppose if I want to test my results with 1 lakh images and I want to record the values. See, as of now, any paper you take, there may be some limitation on the test data, or there may be limitation on the trained data. Forget about trained data. So if you increase trained data, that's not a problem. Someone is okay. See, forget about the trained data. Now, if I want to test my model, as of now in the literature, the CVPR latest paper, suppose assume that in your area tested with 100 images and you want to test with 10,000 images. And if you get, you may get better results. So that is how, if you want to train, so faster time, time to train and the number of images you can try, both can be improved through quantum computing. Rather than just testing with some 100 images or taking time to train the images more hours, you can train the models faster and you can use more number of samples. So that's what parallel processing. Parallel, I can store the information. See here, solve problems fast. Either constructively, if you want to build a model, test a model. Destructively, destructively means in the cryptography, you want to find out a key with the 2 to the power of say 256 combinations are there, and I want to find out whether my algorithm, I proposed an algorithm, and I want to check that if I try which at what, suppose the key assumes that 256 and secure, and if I try all possible combinations, I can break the algorithm. Or when it comes to machine learning and deep learning, I can train with more samples quickly, and I can use more samples to test it. So that is obviously gives edge. So see here, in classical computing, either 0 or 1, but in quantum computing, you will take, this is the state. So that state is combination of 0 and 1. And what is those? These are the probabilities. So the condition must be 1. Okay. So alpha and beta such a way that that will distribute the probability. How much information about this particular variable you are storing, and how much information about this particular variable you are storing. So that is what. So this variable. Now, if you go to classical computing, this can be equal to 0, or this can be equal to 1. That's it. But combination, you are distributing. This is 90% variable I'm taking. This is 10% variable I'm taking, and that is what you are creating a new qubit, and that is having 2 at a time. So you can process. Okay. So now see here, alpha and beta can be 1 by root 2. So if you use 1 by root 2, okay, what this is the 1 by root 2. Equal probability alpha and beta, and what is the condition? Alpha square plus beta square equal to 1. So when we square it, it become 1 by 2 plus 1 by 2 equal to 1, satisfying the conditions. This is alpha and this is beta. Okay, so alpha square and beta square equal to 1, condition satisfied, and you are using this information. That means equal probability, equal amount of this and this you are using to create a variable. Now, suppose if you go with the 2 bits, see here, 2 classical bits if you are using, these are all the combination. Any single variable if you take, it may contain 0, 0, or it may contain 0, 1, 1, 0, 1, 1 combination only. But see here, you are creating a quantum state. See here, 2 qubits in superposition. So your superposition means just importing. Let's say just adding. So then you are creating quantum state. And these all possible 4 states together. So with one operation, you can try all the 4. Whereas here, you have to create 4 such variables to store those 4 values. Okay, see here, process all 4 possibilities in one go. So here, if you do it 4 times, here I can do it 1 time. So this is a magic. The quantum mechanics will do that. It's underlying mass. Okay, don't worry. But we are not going much with that. Okay. So see here, combination. See, qubits. If I qubit is 1, 2 to the power of 1, which is equal to 2, I can use 2 qubits, 0 and 1. If I have 2 square, so I can use qubits 0, 0, 0, 1, 1, 0, 1. Similarly, if I want to use 3 qubits, okay, this one. So 8, 1, 0, 0, 2. So 2 to the power of n combinations, you can try parallelly. See, this is superposition. All 8 into one variable, 4 into one variable, 2 into one variable, all 2 to the power of 1, n into one variable. You can put it and you can try parallelly. Okay, see, the secret to quantum computing is parallelism power. and that parallelism is coming from superposition. What is meant by superposition? Representing these four, these eight into a single variable. So this is entire quantum computing. All four combinations, 2 qubits together, all 3 qubits means 8 together, 4 qubits means 2 to the power 4, 16 together, you can play at a time, parallelly. So with that computing, see here, cryptography, breaking any secure system, chemistry, okay, optimization, anything, huge data. If you have huge volumes of data to be considered to come up with a value, you can use optimization, machine learning, finance. Same thing. Wherever you apply the data analysis is where you can apply machine learning, you can use this quantum computing. The advantage is you can have parallelism. The way you store the data, represent data is completely different. Okay, so before going, I just want to introduce how it is different to ML also. So how it is different to ML. Later we'll come across, see, all those things we can study. What is that is what he added. Okay, so how it works, all those things. Okay, but I just want to introduce quantum gates, circuits, all those things we'll study in tomorrow's class. But I just want to correlate with machine learning so that we can understand easier. So here what happens, we have a model. See, what is my quantum circuit? Same. As I said here, you have a model in the machine learning, and we have the set of features, and features you feed it to the model, and model will give you the output. Same thing we need here also. So see here, in classical computing, we have AND or NOT gates, so you will perform some operations on those inputs. Same here, you will build complex model. That's what you are calling it as a circuit. So you are building the circuit. What is a circuit? Circuit we'll see here. A quantum circuit is a mathematical and physical model that describe how qubits evolve over time. Same thing here. When you give the features as an input, so it will perform some set of complex operations, and data you will generate, right? Same here. So circuit is a combination of gates. Okay, so whatever you want, whichever operation we want to perform by using Hadamard gate, C0 gate, RX gate, there are a few gates. So by using R for rotation, NOT gate, okay, then converting means into qubit. See here, somewhere we will Hadamard gate we use to represent the qubits. Okay, so don't worry all those things. We will again come back. I just want to introduce. Okay, so these are various gates. Combination of gates is a circuit, and you will give the qubits as a information input, and through the gates. So here we have neurons, here we have gates, and the combination of gates is what we are calling as a circuit, and circuit will process the data, and it will give you the output. So underlying concept is same, but the way you are representing the data, the way you are processing the data is completely different. So see here we'll follow the quantum mechanics. What is quantum mechanics? Same thing, but okay, we don't go much deeper. Fine. So it defines a sequence of operations. That's what we are going to apply to an initial quantum state. So here you represent the data. It may be quantum 0, quantum 1, depending upon the complexity of the data. So it may be 1 quantum bit, or it can be a 2 quantum bit, whatever it may be. So it will take the data and see, it will apply sequence of operations. And then you will get a final state that can be measured to get classical outcomes. Same thing. Okay, so quantum circuit is what? The model. Circuit is a combination of gates and process the inputs. So like this. So you have an input. You don't need to worry. Just correlate. So you have an input, and here also you are passing an input. And see, like same x1, x2 are the inputs, and x1 and x2 you are feeding it to the neural network. So x1 you will substitute, x2 you will substitute. And what happens? There will be a neuron. So the neuron, you all know that this is a summation operation, activation operation, right? So like this, we are processing the data. We are processing the fully connected network, and you are giving the output, network output. Same here also. So when you feed in, so RY means it will rotate the data. So next here also you are rotating the data. See, that's what the way you see block sphere. The way there will be a sphere, okay, and the way you operate the data. Okay, so these are the various operations. So here you are performing summation and activation. Same here, it is performing various operations. It is giving the output. Okay, but it is more efficient. It can handle if it rotates, it can able to capture more information. Parallelism is more. So this represents a quantum circuit, often used as a trainable block. So in neural network, what is a trainable block? In neural networks, what we are going to train and what we need to train? Swati?
The model we are using to classify or
No, what is
manifest
hmm, what is trainable? Trainable means what actually it is learning.
the features of the data, pattern in the data.
It is learning the weights.
Weights, it is learning the weights.
These are the weights. So every network, every link is having weights. So these weights it has to learn. Same here also. So here there, what is theta? Theta equal to parameters. Parameter equal to weight matrix and bias matrix. So it has to learn those weights. Same here also. It has to learn theta. That means how I represent, how I rotate the data. See here. So Ry of theta is what it is doing. So whenever it receives the information data, okay, so it is rotating the data some block, and it has to learn the theta. So when I take any information, any data like qubit information, any data, okay, for understanding, say if I given phi 3, rather than the neural network is performing weight transpose into x plus bias, these quantum computing focus on rotating the data. More or less, see, when I do weight transpose into x plus b, it is transforming into some value, some vector. Same here also. I'm using Ry theta. So how much I need to rotate? Is it learnable parameter? So theta 1 and theta 2 are the learnable parameters where I am performing rotation operation at y-axis. See here, what is Ry theta? Is the rotation gate around the y-axis of the block sphere. We will go through what is block sphere and all. So at higher level, we try to understand. Okay, transforms the cubic state. So this is what we are sending, same input based upon the angle theta, so that output has to match. Same way, this is the input, it has to match. So if I want to do that, how much I need to rotate, which are all the operations I need to perform. It's a trainable parameter, just like weights in neural net. So here you have weights, here you have theta. So mathematical, see, this network is like this: cos theta, sin theta, minus sin theta, cos theta.
Rotation in the sir.
Rotation, see, that is how you are transforming the data. Okay, so you are moving the data from one part to another part of the spheres. So here, why you are multiplying with weight transpose into x plus b? So that is what, for each input you are computing the importance, you are computing the weight. Same here, for each input how I have to rotate, so that it will also transform to some number. Okay, so these are the various operations we will perform on the block sphere. For quantum mechanics, we have a sphere, so we assume that these qubits are points on the sphere, and then how we have to convert them so that it will give the correct output. Okay, so here you have to understand the role of theta. So if you keep on changing, the inputs are getting changed. See here, in quantum machine learning, theta is learned during training. Same here. So this theta you have to learn. And how here also a kind of transformation, weight transpose into x. You are multiplying with the weight. Same here. You are rotating. So how you what you are doing here? Somewhere you have to multiply the weights. Somewhere I don't know whether I kept it or not. So what you are doing is the rotation means, see here, what is meant by rotation? You are not rotating, but actually what you are going to do is, suppose in this case, if you substitute the data, okay, suppose r pi means 180 degrees. So if you substitute 180 degrees, if you substitute, then what happens? See, cos 90, okay, this is cos 90, sin 90 1, cos 90 0. Okay, so it will give values, I will show, okay, maybe next class it will get some values minus, okay, sin 90, sin 90 means 1, okay, sin 90 1, this cos 90 0. So if you multiply this with say 1 0, assume the value. Now tell me what is the value here? 0 into 1 0, plus minus 1 into 0 0, which is equal to 0. Next, okay, 1 into 1 1, plus 0 into 0 0, it will become 1. So 1 comma 0, When you multiply with pi 180 degrees, it is becoming 0 1. So in quantum computing, when I say it is this one, quantum bit 0 means it is representing 1 comma a value called as 1 0 in this pair. Next, when I say it is equal to 1 means which is equal to 0 comma 1. Everything is weight matters. Okay, so that's why if I want to transform, see here also, when I multiply the weight into x, it is getting transformed into some other value. Same here, if I want to multiply this, becomes a weight matrix now. So weight, if I multiply this 1 comma 0 is becoming flipping. So so based upon the output, what value I need to get it here, then next step, next step. So the label is y. If I want to get a value of 1, then what should be the values? So that is what we have to learn theta. There it is weight. Clear? So input as how, why we are multiplying with sigma and nonlinearity. So that is how we are extracting the features, transforming the features. Here in quantum mechanics, quantum computing, this is how we have to transform the features. Is it clear? Algorithm. So okay, so that is done. Okay, this also we discussed. Okay, now see here. You can't see all the superposed states directly at a time, all combined to form this one. Okay, magic. Suppose if I toss a coin, assume that suppose this one. So suppose say 0 comma 1. Then what is happening? If I in normal I have only one coin. So when I toss, it will be head, it will be tail here. So when I open it, I can see either head or tail. But in quantum mechanics, what we assume is, okay, there are two coins, magical coins. Assume that head will be there, tail will be there. Okay, tossing. But when you hold it and when you open it, either head or tail will be there. How much percentage? That is what alpha and beta is doing. So the condition is alpha square and beta square equal to 1. So if alpha value is high, I may see that it may contain h, and I can if beta value is high, I may see that it may have j. So that is how at a time two values I can play with it. But when I realize it, it is single value. So okay. So when you measure, the system collapses randomly to one of the possibilities, either H or T. The chance of each state is based upon the amplitude. What is amplitude? Alpha and beta are the amplitude. Okay. So all states here, when I say 1 by 2 is what the alpha we are using. So 1 by 2 whole square is 1 by 4, which is equal to 25%. So 4 values out of these 4, one value will realize. That is what we are going to store it here. But for operations, all 4 will be available. 4 parallelly I can use. Okay. So that is what I just want to introduce. What makes quantum computing differ when compared to classical computing? Okay. So the way we represent the data, the property of the data. First, the way we represent the data, the property of the data, like superposition both at a time. Second one is the way we operate on the data. So as we have seen, we are mainly here, we are performing the rotation operation. There in the neural networks, we are performing the scaling operation, weighted dot product. So dot product is the main operation in machine learning. Here we are performing rotation. The model is the neural network. Here we are calling it as a circuit. Circuit is a combination of gates, and neural network is a combination of neurons. But every part, it is somehow transforming the data. This one also transforming the data, so that it will learn how I can map the set of inputs to the label. Clear? Okay, so this is what his slides. So quantum mechanics, we are following the laws of quantum mechanics. Okay, next, see here, and that is how all these things happen. See here, algorithm reduces the complexity. See, algorithm came up with a quantum algorithm to factor every large numbers in polynomial time. Factors, I want to compute the factors. What is factor? Say suppose 15, 5 into 3 is factor. Okay, 1 into 15. So I need to list all the factors. Suppose if I want to list it for 2 to the power of 276 number, for this number I want to list the factors. Is it possible for us to do it with classical system? Not possible. See, assume for 2 power 10, which is equal to 1024. So 1024, if I want to do it for classic factoring, okay, so I need to split it. So how many possible combinations are there? Now, if I want for 2 to the power of 276, assume how many, some crores of combinations will be there. So I want to try all those. I want to print all those. It's not possible with classical computing. It's always with quantum. And I can find out then, see here, with the big O of square root of n complexity. The classical algorithm may take big O of n or big O of n square. I can always reduce the complexity drastically if I use quantum computing. See here, quantum circuit, that means the model can simulate any classical computation. So whatever you are doing with classical machine learning, complete machine learning, you can use it for quantum circuits. Okay, so somehow, see here, developed a quantum search algorithm, speeds up unstructured search. Randomly you are searching. So classical system will take big O of n. See, this big O of n, if you see that, suppose if it is say 100, and if you make it quantum, it is big O of 10 only, very drastic reduction. And now see, if I keep on increasing the number 10,000 times, 10 to the power of 6, square root means square, that means 10,000, 1,000. So I can do it with 1,000 only. So what, see here, 1 lakh steps I need here, I can do it with 1,000. So like that, it will drastically reduce as the computation time. So now you have to think how I can bring in quantum computing into my task. Either apply your problem to quantum computing or add the patch of quantum computing here, because it is booming now. If you try, definitely it will help you. So this part somewhere, how I can add this quantum computing by more testing. Okay, parallelly I can try more combinations. Okay, so you can think. See here, RSA encryption algorithm, which is hard to break using classical computers like this, finding the powers and all for 2 to the power of 4, 258, 512, etc. Key length. I can use quantum computing and I can break out. I can find out, suppose this is 1, this is 2 to the power of 258 number. Somewhere I can find out the correct one and I can break the key because of my quantum computing. Okay, so that's what, see, modern computers, or it is using classical physics. So what is meant classical physics? Like voltages, bits 0 or 1. Okay, Boolean logic, either 0 or 1. And what quantum computer says? 0 and 1 proportionately. So that's why both states, more information I can capture. Okay, so what is the advantage? See, from quantum mechanics, what we got? Superposition, entanglement, measurements. See, qubits can be correlated in strange ways. Okay, a bit can be in multiple states. Both. We'll study what is superposition, entanglement, etc. Okay, so see here. So this one, I just what is bit here, and how you will represent the information. Okay, so just now we have studied. See here also qubit. When qubit is 1, these are the two values. When we say in classical terms, it is 0 1. When we say qubits is 2, all 4 combinations. Qubit is 3, all 8 combinations. So that is how we represent the data. That's it. Okay, so data representation, see here, we just studied the bit of data is represented by a single atom, that is one of the two states denoted by this and this. Okay, so see here, somehow they are using information and they are using circle. See, combination, superposition is what? Combination satisfying the property. Both, I'm considering both the bit information. Okay, so see here, 3-bit info, all these things we will study. So I just want to give the information. See, it's complete gates. Okay, so how you will feed the data and gates, and you see here quantum gates. Okay, and the combination of quantum gates gives you the circuit, various states. Okay, so various gates we can study Hadamard. Okay, so somewhere I have explained Hadamard gate, etc. All those things we'll study. So here, see Hadamard gate. Okay, so see here, Hadamard gate, rotation, operations. So these are very different compared to classic computers. Okay, so operations and data, we can create more circuits. The data is moving. Okay, data information, and you are transforming the data. See here, sometimes you may keep it both, or you may take only one. Somehow you can manage. You can build complex circuits, not gate or gate, and you can combine them to form a complex circuit. See here, multiple input output combination, three inputs, three outputs. Okay, so like this we will perform the various algorithms. Okay, and then we'll try to get the output. Okay, then we will study some maths also. All those things will help you to understand the power of supercomputing. Okay, so any doubts? This is budding, like starting state. So if you can try to apply this quantum computing, okay, definitely it is going to help you. Okay, mainly for Swati and Sweta, apply quantum computing. Okay, somehow you have to reduce. Somehow, like this is advantage. My model, in like suppose using quantum computing to extract the features, because we are using qubits, right? So input, normal classical inputs, I will give it to quantum model. Quantum model will give me features. So those features may be efficient, and I can proceed with my classical model or completely quantum. So that's how you can plan. Okay.
సార్ ఎంఎల్ మోడల్స్ అన్ని ఇలా ట్రై చేయొచ్చా సార్ క్వాంటమ్ లో?
Yes, everything is quantum. See, that's what everything is quantum. See, he is doing. I suppose, see, I can just type quantum CNN. So quantum CNN is the quantum convolution neural network.
ఎల్ఎస్టిఎమ్స్ కి అప్లై చేయొచ్చా సార్?
LSTM is also there. No need to worry. So quantum LSTM, whatever you want, quantum LSTM.
అండ్ ఇందాక మీరు రొటేషన్ అనేది రొటేషనల్ మేట్రిసెస్ లాగా, లైక్ మేము లోకల్ కోఆర్డినేట్స్ ని గ్లోబల్ కి మార్చడానికి మల్టిప్లై చేస్తాం జనరల్ గా సార్,
Yes, yes,
ఫిజిక్స్ లో లాగా
yes.
రొటేషనల్
అంతే,
ట్రాన్స్ఫార్మ్ ద కోఆర్డినేట్స్.
అంతే సేమ్ ఆ ఫిజిక్స్ నే వీళ్ళు కొంచెం క్వాంటమ్ అని పెడుతున్నారు అంతే. సే క్వాంటమ్ లాంగ్ షార్ట్ టర్మ్ మెమరీ జస్ట్ స్టార్ట్ 2020లో. సో యూ కెన్ యూస్ QSTL, ఈ QLSTM వాడి. సి LSTM అండ్ QLSTM హౌ టు డూ దిస్. సి దిస్ ఈజ్ నార్మల్ వర్క్. సో క్వాంటమ్ లో అయితే ఎలా చేయాలి? దిస్ ఈజ్ క్వాంటమ్ గేట్స్ కదా. సి వేరియేషనల్ క్వాంటమ్ సర్క్యూట్స్ ఇక్కడ ఎలా ఉంటాయి, హౌ యూ గెట్ ద డేటా అంటే సేమ్. అసలు ఇది మనకు అవసరం కూడా లేదు, జస్ట్ యూ కెన్ టైప్ ద కోడ్. ఓకే, సో QLSTM పైథాన్ కోడ్, యూ కెన్ గెట్ దట్ కోడ్, దట్స్ ఇట్, యూ కెన్ యూజ్ ఇట్. క్వాంటమ్ కోడ్ ఉంటుంది, QLSTM, క్వాంటమ్ LSTM అంటే.
అండ్ లో జీపీయూస్ ఉండాలా సార్? కంప్యూటేషనల్లీ కష్టం అంటున్నారు, అలా ఏం కాదా సార్?
See here, see if you see now, everything is there. See quantum circuit, you can create, transpile, assemble. Just it created quantum state, summate, measure, and create చేసింది. You got the output. Okay, and Python is having the library, quantum computing on the same, ante developed by IBM.
ఓకే.
So you can use this to create the circuits, qubits and type in the how you ante. So it's same Python code, but your question I need to check, because see మనం చేయగలమా లేదా అనేది it all depends upon the data. అంటే GPU అంటే ఒక మాస్టర్ GPU ఉంటే చాలు. ఐ డోంట్ ఈ ఇమేజ్ బేస్డ్ అవన్నీ కూడా we may not use solve it using this one, collab. But have a decent GPU, you can go ahead, see how you can create the quantum circuit. Let's see how the what are the features, everything. LSTM అన్నీ ఉన్నాయి దీంట్లో. It all depends upon the circuit దీని మీద అనమాట, how డేటా అనేది. సో సి క్విస్కిట్ ఉంది కదా, సేమ్ క్విస్కిట్ IBM LSTM అంతే. how to instantiate neural networks, forward pass, backward pass. Everything remains same.
Okay.
ఓకే, దట్స్ ఇట్. ఇన్పుట్ అవుట్పుట్ మళ్ళీ ఎట్లా దాన్ని ఇది చేయాలి కొంచెం మారుతుంది. అండ్ ఇఫ్ యూ ట్రై టు అండర్స్టాండ్ డీపర్ వే, దెన్ ఆటోమేటికలీ యూ కెన్ సెట్ ఇట్. దీని యూస్ ఎవ్రీథింగ్, నెంబర్ ఆఫ్ ఇన్పుట్ ఫీచర్స్ ఫర్ ఎస్టిమేషన్, ఎవ్రీథింగ్, ఆల్ థింగ్స్ వీ కెన్ డిస్కస్. సో ఇది చేసినప్పుడు సమ్వేర్ ఇఫ్ యూ కెన్ ఏబుల్ టు రెడ్యూస్ ఆర్ ఇఫ్ యూ కెన్ టేక్ దోస్ డిఫరెంట్ ఫీచర్స్, సో టేక్ LSTM ఫీచర్స్, గివ్ ఇట్ టు క్వాంటమ్ LSTM, హౌ క్వాంటమ్ అట్లా సమ్హౌ యూ ప్లే ఎన్సెంబ్లింగ్ hybrid LSTM and classic and quantum, definitely it will work.
ఓకే సార్.
Okay, so it's a long short term
Yes, sir.
memory.
రీఇన్ఫోర్స్మెంట్ లెర్నింగ్ ఈ సెమిస్టర్ చెప్పేశారా సార్?
Uh-huh.
రీఇన్ఫోర్స్మెంట్ లెర్నింగ్ ఈ సెమిస్టర్ చెప్పేశారా సార్?
Reinforcement
ఆర్ఎల్
RL జరుగుతా ఉంది. ఇది మెయిన్ బిట్స్ లో RL RL
చెప్పాల్సింది సార్.
RL జరుగుతా అంటే వాళ్ళు రానిరు కదా.
ఓకే.
ఇప్పుడు మన క్లాస్ ఇట్లా, సో ఇవి జరుగుతుంది అనమాట. మాంటే కార్లో మెథడ్స్, తర్వాత ఇవన్నీ MDP అయిపోయింది, డైనమిక్ ప్రోగ్రామింగ్. ఓకే, ఇవి జరుగుతా